air with a density of 1.2 kilograms per cubic meter blows parallel to a flat plate upon which a boundary layer grows. The plate is 10 meters long in the streamwise direction and 4 meters wide, normal to the page. At the leading edge of the plate, the airspeed is uniform at u infinity equals 10 meters per second. The velocity profile is measured at the end of the plate and is found to vary with distance y from the plate according to u equals u infinity times y over delta to the 1/7, where delta equals 170 millimeters is the boundary layer thickness. Determine the viscous force on the plate. Consider only the flow over the top surface of the plate. The dashed line labeled A is a streamline in the flow. So here's a picture of this plate. Here's the plate. It's 10 meters long and it's 4 meters wide in and out of the screen. There's a uniform 10 meter per second velocity approaching the plate, and it's flowing in this direction. By the time it gets to the end of the plate, which is 10 meters away, the viscous force on the plate has slowed the air down, so now we have a velocity profile. And the equation that describes this velocity profile is this 1/7 power law given here. The boundary layer thickness of 170 millimeters is shown on here. So that's the thickness of the boundary layer. In other words, the distance away from the plate where the velocity has been reduced. Notice that up at the edge of the boundary layer up here, where y is equal to delta, u will be equal to u infinity. So this local speed up here is 10 meters per second as well. Now it also talks about this dashed line being a streamline in the flow, and that's going to be an important consideration in this problem. Now, what we've been asked to find here is the viscous force on the plate. So because we're looking for a force, we want to do a control volume analysis where we focus on conservation of linear momentum. Because conservation of linear momentum talks about forces giving rise to a change in momentum of the fluid. Well, that's what's happening here. This fluid has some momentum. A force acts on it. In this case, the force due to viscosity on the surface of this plate, and that changes the momentum of this flow. In fact, it reduces the momentum because it's slowed down here. So it's a control volume analysis. So our given information, we will just use the diagram that's given, and essentially everything that was given in the problem statement is also given on the diagram here. We may add a couple of things to it as we go along, but we want to make clear what we've been asked to find. And what we're trying to find is the viscous force. And it's the viscous force on this plate. So we want to first of all identify our control volume. So let's set up a control volume here. So because we want the viscous force to be an unknown in our equation, the control volume I'm going to set up is going to go right along the surface of this plate. Okay? So there's going to be a shear force exerted on that surface of the control volume. Then I'm going to go straight up here because I know the velocity there everywhere. And I'm going to go straight up here because I know the velocity there everywhere. And now the top of the control volume is going to be this streamline A. And the reason I'm doing that, the reason I'm choosing that streamline to be the top of the control volume is, remember, there's no flow across a streamline. So there's no flow across that portion of the control surface. So this entire control surface that I've drawn, there's an inlet here and an exit there. And that's all there is. Okay? So we'll begin with our list of assumptions. And again, we'll make those assumptions, or we'll add them to the list as we make them. The analysis. We'll begin here. So again, we've already recognized that this is conservation of linear momentum. So we'll begin with the linear momentum equation. Body force term is first. Then the pressure forces, viscous forces, plus reaction. So those are all the forces on the left-hand side of the equation. Next is the unsteady term. So the rate of change of the momentum of everything in the control volume. And then finally, momentum fluxes across the surface are given by this. So a complete general form of the linear momentum equation. Now, term by term, let's take a look at this. First of all, the body force. Well, again, this is a problem where we don't even know the direction of the body force. And regardless, the body force is the weight of everything in the control volume. And all there is in this control volume is air. So it's going to be a very small body force, and regardless, we don't even know what direction it's in. So we're certainly going to neglect the body force. And that simplifies our equation by eliminating this term. Next thing we're looking at is the pressure force term. So there's air flowing over top of this plate, but notice that everywhere on our control surface is just exposed to atmospheric pressure. So the pressure is the same everywhere on the control surface, so this is 0. So we'll just say here we have uniform pressure on the control surface. And the consequence of that is the net force is 0. Next term we see here is our viscous force. And this control volume, there is certainly going to be a viscous force where the air is flowing over this flat plate. In fact, that's what we're looking for. So that's certainly a viscous force. There isn't going to be any viscous force at this inlet because the air is just crossing perpendicular across that line. Likewise, there isn't going to be a viscous force at the exit here because the air is just crossing perpendicular across that line. We're also going to assume there's no viscous force out here. This is a streamline of the flow, so it is possible that there's a tiny bit of viscous force there if the velocity just outside is different than the velocity just inside, but compared to the viscous force down on this plate, that's going to be very small. So we're going to neglect viscous forces along the streamline. So we'll put that in the assumptions list. Neglect viscous forces at top, I'll say, of control volume. So in terms of our equation, we certainly keep that in there, but this is recognizing that when we solve for that, that's going to be the viscous force on the plate. Next thing we see is a reaction force. Notice the control volume we chose does not cut through any solid object, so that reaction force definitely has to be 0. So I'll just say here no reaction force, just to clarify that. Next term we have to look at here is the unsteady term, and there's nothing changing with time here, so we'll say steady state. Next term we have is momentum transport across the surfaces, and as we take a look at this, control volume has an inlet here, and the inlet is uniform, but the exit is non-uniform. So we can make the uniform flow assumption at the inlet, but we can't make it at the exit. Now the next thing we'll recognize here is the viscous force is going to be in this direction. So I should add another coordinate axis on here. Y is the distance away from the plate. We'll call this x, the streamwise direction. So the force we're after is certainly in the x direction. So what I'm going to do is just extract just the x component of this out. So I'll take the x component of this force, just call that F sub x, and then we only need to consider the x component of this. But everything is flowing in the x direction here anyway. So first of all, the exit, which is non-uniform, we can take the density outside, and we'll have an integral over the surface, and we'll figure out what those limits are in a moment. The velocity here, we only need to consider the x component of that velocity, and that is just given by this equation here, right? This is the x component of velocity, that equation. So we put that equation in there. So that velocity is u infinity times y over delta to the 1/7. So that's this velocity. And remember, we're just taking the x component of it, so it's not a vector anymore. V dot n at the exit. So that's the velocity. The unit normal here, remember, is like that. So v dot n is just equal to v. So this expression for the velocity is also v dot n. So we just have this same thing over again. So I'm just going to square this and square this. So this is essentially the velocity squared. dA, so the area that we're integrating over is this. So dA is going to be dy dz. So dy dz. Limits of integration on y are going to be 0 to delta. Limits of integration on z will be 0 to w, the width of the plate. So that's the exit. And we have to integrate because this velocity is a function of y. Now we don't want to forget the inlet, but it's a uniform inlet. So there we can just say minus m dot at the inlet, which we'll label as 1, I guess. So this is 1. This, I guess, is 2. So m dot 1 times the velocity at 1. But remember, we're extracting just the x component, so we just need the x component of the velocity at 1 here, which is u infinity, or 10 meters per second. So that's what we have to work with. So we can continue working with this. The force in the x direction, density. Notice the first integral here, the outer integral, is with respect to z. Nothing in here depends on z. So that can just evaluate right away to w. This u infinity squared is a constant. That can come outside of the integral sign. In the denominator here we have delta to the 2/7. That can also come out of the integral sign because that's a constant. And we'll leave in our integral from 0 to delta just the y part of this. So this is y to the 2/7 dy. Minus the mass flow rate here. We can represent the mass flow rate in terms of other variables here, in terms of u infinity, this distance, and the width of the gate, which we've already called w, and of course the density of the fluid. So I'm going to label or dimension this distance, because we don't know what that is yet. Notice that wasn't given. I'm just going to call that h for now. But the mass flow rate in this we can put down as rho times the velocity, u infinity, times the area, which is h times w. So all of that stuff is the mass flow rate. So density times the velocity times area. But then we need to multiply it by velocity again. So I'll just put a squared there to get that. So that's our expression for the force in the x direction due to viscosity. So we'll continue to work with this, do the integration. So fx, we have rho w u infinity squared over delta to the 2/7. And this becomes delta to the 9/7. So we're adding 1 to that, divided by 9/7. So 9/7 minus rho u infinity squared h w. Now, if we think about what we know and what we don't know in this whole thing, the density was given as 1.2 kilograms per meter cubed. That's fine. W is given as 4 meters. Delta is our 170 millimeters. U infinity is 10 meters per second. Delta, again, we know. So we know everything in this. We can solve for a number for that if we want. Next thing we have over here, we have density, which we know, U infinity, which we know, W, which we know. But the problem we run into here is we don't know this H. So we don't quite have everything that we need to plug into here and solve for a number for this force. So this H presents a problem. So let's go back to our diagram and remind ourselves what that is. That's this distance here. Okay. Well, if we take a look at this, one conservation law that we haven't used yet is conservation of mass. So we know this distance, 170 millimeters, and we know an equation for this velocity profile, so we can calculate the mass flow rate out of there. Because this is a streamline, we know there's no mass flow across it. So that'll allow us to calculate the height of this. So conservation of mass is the thing that is going to give us this h. So we need to set our linear momentum equation aside for a moment. So we'll just be coming back to this once we get this h, and we need to consider conservation of mass. So we can say here that we need h. And where's that going to come from? Conservation of mass. So general form of conservation of mass equation is what we always start with. So it says 0 equals the rate of change with respect to time of the mass in the control volume. And that's the integral over the volume of rho dV plus the integral over the surface of rho times VR dot N dA. So again, it's a steady problem. It was steady for conservation of linear momentum, certainly be steady for conservation of mass. And also, this surface integral, the inlet is uniform, but the exit is non-uniform. So we do the exit first, and we set up the integral exactly the same way as we did for momentum. Only difference is there's no v in here. So density is constant, integrating from 0 to w and 0 to delta. So that's with respect to z and y. The velocity goes in here, so Vr dot n, u infinity, y over delta to the 1/7. So that's our velocity profile, times dy dz. So that's the non-uniform exit, minus the mass flow rate at the inlet, and that's density times velocity times area. And that all has to equal 0. So again, we can pull out everything that's constant here, and we can do this z integration right away because nothing in there depends on z. So that's rho w, u infinity is constant, and in the denominator, delta to the 1/7 is also a constant. And we still need to integrate from 0 to delta, y to the 1/7 dy. And that's minus rho u infinity hw. That all has to equal 0. So density w u infinity over delta to the 1/7. So this is delta to the 8/7 divided by 8/7. So divided by 8/7 minus still rho u infinity hw equals 0. Notice that delta to the 8/7 divided by delta to the 1/7 is just going to be delta. And so lots of other stuff cancels here. Density cancels on both sides. W cancels on both sides. U infinity cancels on both sides. So we just get that h is equal to 7 delta over 8. So the h is 7/8 of delta. If we go back to our diagram, we can see that h has to be smaller than delta. This distance is delta. The velocity is higher here, so the area has got to be smaller. And it turns out that is 7/8 of this. That's what we've just found. So now we're ready to go back to our linear momentum equation. So we can begin working with this equation again. And we can simplify that a fair bit too, because there's a whole bunch of things that occur in both of these terms. So we can rewrite that. So the force in the x direction is rho w u infinity squared. So that occurs in both of those terms. And then we just have 7 delta over 9 minus h. So we're going to take our expression for h and put it in there. So this is rho w u infinity squared, 7 delta over 9 minus 7 delta over 8. So now we have everything in this expression. And we can simplify it a little bit more by combining these terms together. So that's going to be equal to rho W U infinity squared. Factor delta out of this, and then take a common denominator here, which will be 72. So this will be 56 minus 63. So our final expression for the force in the x direction is going to be negative 7 over 72. So that's coming from here. So notice it's negative times rho W U infinity squared delta. And notice it's a negative number it's come out to. So does that make sense? Remember, this is a force on the control volume. So the force that this plate is going to exert on the control volume is going to be in that direction, which is our negative x direction. So that does make sense. So all we have left to do here is substitute the numbers in to get this force. So let's do that. We have negative 7 over 72, constant out front. We have 1.2 kilograms per meter cubed. That was given as our density. W was given as 4 meters. U infinity was 10 meters per second. So that's 10 squared meters squared per second squared. So that's our velocity squared. And then the delta was given as 170 millimeters. So that will be 0.17 meters. Multiply all of that stuff out, and we get this force equal to minus 7.93 newtons. So the force, the viscous force on that control volume by the plate is 7.93 newtons.